Hello everyone and welcome to this lecture. So far we have only dealt with single valued functions for complex variables, but today we want to take a look at multivalued functions. So let us start with an example. So let's call this an example. And the first example that we are going to consider is f of z is written as square root over z, that is z to the power half. You can also call this f of z as w if you want, so that you can relate with our previous lectures that this is a map, that is if you take some z it will correspond to some w. So the next thing that we are going to do is that we are going to represent z in the polar form, and if you do that it will be r e to the power I theta, but there will be an additional I 2 pi n, where this n is equals to 0, plus minus 1, plus minus 2, plus minus 3, and so on, right? And what we will see in a few seconds is that this square root over z is actually a multivalued function. So use this result from here. Let's call this equation 1, and we want to put this into our equation A, that is we want to put the value of z, or the polar representation of z, and we want to see what happens to w, sorry. So w is just square root over z. Now we want to put r e to the power I theta plus 2 pi n, and then take the square root. This will just be square root over r, and let me detach these two parts, that is theta and 2 pi n. So this will be e to the power I theta by 2, and this part, that is the 2 pi n, will now be e to the power I pi n, and here this theta is our principal argument. You can recall this from your previous lectures. So technically we are done, and let's try to see what happens if we draw the Argand planes. That is, this will be our z plane, and here we want to draw the w plane. These are real parts, this is the imaginary part. Similarly over here, and let's say this z is somewhere over here with some principal argument theta, and what we want to do is that we want to make a full rotation that will correspond to n equals to 1. And if you do that, you can see from this equation over here, that is equation 3, let's call it equation 3, whenever z makes a full rotation, our w over here, it will make 1/2 of it, that is it won't cover the entire w plane, because if you just put n equals to 1, you will get e to the power I pi, which is just minus 1, and this will correspond to minus square root over r e to the power I theta by 2, right? So it's only covering 1/2 of the plane from here. So here n equals to 1, and this is the mapping. And what we would like to do is that we would like to cover the entire plane for w as well. But to do that, you now have to make another 2 pi rotation, and then it will go back to its original place over here. So in case you get confused by what is happening in the diagram, let me just use equations to make you understand what is happening here. So the thing you want to do is that you just want to write this whole thing, that is our equation 3. So when you make one rotation, that will correspond to n1, n equals to 1, you will get w, let's call this 1, and you are getting square root over r e to the power I theta by 2 e to the power I pi, but this is just minus 1, so you are getting square root over r, there is a minus in front, e to the power I theta by 2, right? Okay, and I want to now go for n equals to 2, and this will give me e to the power 2 pi I, and this is just what? This is just 1. So we'll have square root over r and e to the power I theta by 2. And similarly, if you go for n equals to 3, we will have w3 as, you can easily see that it will be 3 pi I, and this will again correspond to square root minus square root over r e to the power I theta by 2. For n equals to 4, we'll get square root over r e to the power I theta by 2, and so on. So you can see that the value for w is now multivalued, that is one time it's plus, one time it's minus. So this is the thing, that is the multivaluedness that we wanted to talk about in the first time. And whenever this happens, you are from your lectures on analytic functions, you know that they have to be single valued, they cannot be multivalued, right? So there is something going on over here. And the next question we ask is that, is it possible to make this function analytic? That is, we want to preserve the analyticity, and to get some ideas, now what we will do is that instead of rotating around the 0 point over here like this, we want to shift z. That is, let me just draw the diagram first. So again, this is a z plane, don't get confused. And let's say this is the real number 2, and we want to draw a unit circle. So this will be 1, this will be 3. Let's try to draw a circle over here. And now, instead of rotating around the 0 point, the origin, we are now going to rotate around the point 2. Also, this is a unit circle, so the radius is 1, right? And let's say I want to start from over here. Okay, let me just get rid of that. Let's say this is my starting point, or equivalently you can just start from here as well. So instead of just over here, let me start from point A, and let's call some points B, C, D, and let me choose some colors and draw something, and then I will explain this to you. So again, recall that we are dealing with a function that is w is equals to square root over z, right? And it was written as r square root over r e to the power I theta by 2, and we had this e to the power I pi n, right? And now in this picture over here, where we are rotating around the point 2, we can start from A. So let's start from A. This is our starting point. So again, let me just write that starting point. And we want to see what happens to W as Z moves along this circle, that is circle A, B, C, D. So we will start from this point A, and the idea is to just go around the circle and see what happens to W. So first thing we are going to do is that we are going to start from A, and let's have z of a as 3. You can easily see it from the graph, and for that wa will be just square root over 3, because the argument for this 3 is just 0. Then you'll have zb. It will be denoted by 2 plus I. You can easily get the coordinates, that is 2 and I over here, that is 1, it's a unit circle. And you will have wb equals to square root over 5 e to the power I pi by 4. And then you'll have note something, that the reason I'm writing I pi by 4 is coming from this theta by 2. So you are not this picture is the z plane's picture, but we are also calculating the w over here, and we are not drawing any picture for w. We want to see without any picture that what happens to w if you make a full rotation around this 2 point, that is this point over here. And then we can go to zc, and this is just 1, and w of c will just be square root over 1, which is just 1. And we can have zd, and zd will be 2 minus I, and we'll have wd as square root over 5 and e to the power I minus pi by 4, this one. And this is easily verifiable, because you can see any number in this quadrant, the principal argument will have a minus sign in front of it. So after this d point, that is z of d, okay, just d is understandable, though I've written capital over here, but it doesn't matter. So after this, again see from this graph that when you are at d and you are still moving anti-clockwise, you are now going back to a, and you are returning to your original value. So this time, when you took a path around this circle that was centered at 2, 0 to be precise, you are not getting the multiple valued thing that you got before, that is the thing that was happening over here. So this is a good thing, and at this point you might ask, what is happening? What is happening when we took the path or took the circle centered at 0, centered at z equals 0? And what is special about this 0? To give you some idea, let me just state the idea, and we'll discuss the details in the future videos. Is that for the function square root of z, this 0 is the point that acts like a branch point. So when you enclose the path around it, that's you complete a full circuit around it, your functions get multivalued. But here that was not the case, because this 2 is not a branch point, and we'll discuss more on branch point and something called branch cuts, and how we can make our multivalued function single valued so the analyticity is preserved, and so on. We'll discuss them in the next video. So thank you.